Thank you, Brent. Appreciate that. Well, tonight we're really pleased to have Rick Miller join us to give this presentation. Rick received a PhD from UCLA in 1975. The degree was in geology and emphasis on micropaleontology and stratigraphy. His research and publications were involved in studying microfossils called conodonts from the Southern Basin and Range province of California and Nevada. Now, I looked up what conodonts are this afternoon and found out that they are teeth-like fossils from eel-like creatures. Most of Rick's teaching career was in California State University, Northridge, and then primarily San Diego State University. He took an early retirement and moved to St. George in 2001. By the way, this is where our daughter lives, and so we've become quite familiar with that area. He's continued to teach mostly volunteer community programs at Dixie State University at the Institute for Continued Learning and Community Education. He has written numerous articles about the geological wonderland of the area, including a self-guided trip to the St. George area. We're going to provide you in the next newsletter a link to these particular this link, and it has many interesting write-ups about the geology of St. George and beyond. Now, Rick's ICL lecture, which I actually took part in last winter, was a 9-week extravaganza, which he's going to try to condense tonight into an hour. Good luck. But it was a great lecture series. Rick is a fantastic speaker and very entertaining and captivating. But he inspired me to organize this field trip and for October or sometime in the fall, but we think October. And in fact, he also helped me locate a guide. And so we now have a guide for the trip. And I haven't asked Rick to do this yet, but I'm hoping that while we're there in St. George, he might join us for a day or so. Anyway, tonight's talk will be on the geology of the greater St. George area, which it is a geological wonderland. I can attest to that. And he'll also discuss links to the surrounding areas such as Canyon and Bryce and the Grand Canyon. So without any further ado, I'd like to introduce Rick and turn it over to you. So Rick, go right ahead.
Hey, Rick, you need to unmute yourself.
You guys see us yet? Oh, let's get rid of this too. Do we unmute?
Perfect, you're good.
Okay, and so I'm going to get rid of these if we can. I'm removing some images. Come on. All right. Okay. All right. Everything looked good. There's just my face on the screen and the picture.
Yes.
Okay. So we'll go ahead and start. I wanted to point out to begin with is that I'm over at Dr. Rob Kramer's house, that he volunteered to feed me dinner and allow me to use his equipment to present this because I don't have any access to Zoom really that I want to deal with at home. So it's courtesy of him that we're doing this. So what we're going to end up doing tonight is not only condense 9 weeks into an hour, but we're going to condense 2 billion years into an hour. So I decided to leave out just a few things. Anyway, if you look at the geology around St. George, basically everywhere you look, there's geology. All right, we have everything from world-class anticlines to world-class fossil locations to an amazing mountain called the Lacquer Lift and a variety of different geologic hazards, dam failures, rock falls, floods, good stuff, right? It's a pretty interesting place to live. We even have volcanoes. So we're going to kind of work our way through this and see how it works. And the question then becomes, why are we so lucky? Why do we have all this good stuff? And the answer is basically because of energy. And it turns out that Earth runs on 2 sources of energy. They're both nuclear. One is solar energy, which is nuclear fusion, and the other is internal energy, nuclear fission. And those 2 sources of energy essentially interact at the surface. So we get to enjoy things like earthquakes, volcanoes, storms, and all kinds of good stuff, courtesy of all this energy. So weathering, erosion, floods, storms, nuclear fusion, solar energy, earthquakes, volcanoes, mountain building, internal nuclear fission. It turns out, and this is fairly new, in fact, when I graduated with a bachelor's degree in 1965, the term plate tectonics didn't exist. Okay, so this is fairly new stuff geologically. Basically, the hypothesis was first proposed in the mid-1960s, and it has now, because of extensive research, become a theory. And it's a theory that explains pretty much how the Earth operates and how it works. And this diagram and the following ones illustrate why there's so much geology exposed in the western part of the United States. So what we're looking at here is what is known as the Mid-Atlantic Ridge Spreading Center. And this terminology basically didn't exist either when I was an undergraduate. But what it means is this. What we see is an ocean that's literally spreading apart at the center. And one of the interesting things about it, if you go drill in the Atlantic Ocean, which they started to do in the 1960s, you'll find that there are no rocks making up the floors of the mid-Atlantic, of the Atlantic Ocean that are older than 180 million years. And that doesn't work very well because we know up in places like Greenland and northern Alaska and such, there are rocks that are almost 4 billion years old. So how is it that the oceans could be so young geologically and the continents so old? Very strange thing, and it took a while to figure that out. So here's a US Geological Survey, basically a relief map of the United States. And what you can see is that essentially the left side, or the west side, if you like, of the continent is a mess. The heartland, nothing much going on. And over here on the East Coast is the remnant of something that probably looked like this maybe 300 million years ago. Okay? So what we're seeing is basically a collision between a North American lithospheric plate and the Pacific Ocean lithospheric plate. And this is essentially part of the spreading of the Atlantic Ocean. So we're going to look at a cross-section, roughly the latitude of St. George, and there is St. George right there, approximately, okay? And so this is kind of a cartoon cross-section illustrating how radically different it looks when you cut through the surface. Here's the Pacific Ocean, and we have plate movements. And then we have a variety of things. San Andreas Fault, the Sierra Nevada Mountains, the Basin and Range, the Colorado Plateau, the Rocky Mountains, the Heartland, and then over here, the Appalachian Mountains. And I felt bad by leaving this out, so I added something to it, okay? So this is Dairy Queen land. Anyways, when we look at this in more detail, geologists have basically developed what we call geological provinces. For example, here's the Sierra Nevada. It's a very distinctive feature, and it's considered the rocks and the age its own province. And associated with that is the Mojave Desert, the Basin and Range, the Intermountain Fault Zone, which separates the Basin and Range essentially from the Colorado Plateau. And over here, we have the Rocky Mountains. And when you look at this map, you notice that whatever this location is, there apparently is nothing there. They didn't bother to put anything on the map. And I know that might hit home, but just joking with you. But at any rate, you can see quite a contrast in not only the topography, but the geology. The rocks of these provinces are different in age, different in structural orientation, different in fossils, and so on. So they're very distinctive features. And there's St. George, sitting right on the boundary. So what we're going to look at then tonight for the rest of this talk is essentially a study area that includes the Grand Canyon, Zion Canyon, and Bryce Canyon. How does this, what happened here? Okay, there we go. How does this impact the geology of Utah and northern Arizona, all this activity? And of course, I put this in here, right? Curious minds want to know. Nice little kitty. Okay, here's our study area: Grand Canyon, Zion, and Bryce. And St. George is tucked in right over here. If you look at a map, if you go online and look at a map of all of the national parks and monuments in the United States, the vast majority of them are in the western part of the country. And the reason for that is basically because of plate tectonics. So here we have the Grand Canyon. Here's Zion, and here's Bryce. And I put them basically in order of their geologic age. The oldest rocks that we're going to look at tonight are right down here at the bottom of the Grand Canyon. Essentially, the youngest rocks at the national parks are at Bryce Canyon. And then we sneak in St. George. All right, and it turns out we're going to come back to St. George way up here again later on. All right, so there's a kind of a snapshot of what we're going to do. So we start down here, and roughly 2 billion years later, we're going to end up in here. So here's kind of a breakdown of what we're going to be seeing. There's a modern geologic timescale, and I superimposed on it some numbers. Basically, the origin of the Earth, the beginning of Phanerozoic time, beginning of Mesozoic time, the beginning of Cenozoic time, and right here in the present time, okay? The oldest rocks we're going to look at are a little over 1.8 billion years old. And they occur at the bottom of the Grand Canyon in what is known as the Inner Gorge. And this represents essentially the succession of rocks at the Grand Canyon. The areas that don't have this color represent unconformities, which we're going to talk about some more a little bit also. Then from the Grand Canyon, we go right over to St. George, and we find equivalent rocks. These rocks correlate in geologic age and lithology. And then here's the section of St. George. And then we bounce back over to Zion, and some of the rocks at Zion match up and correlate with some of the rocks at St. George. And then we go to Bryce. And then we come back to St. George, and there's some rocks here in St. George and some rocks here in St. George. Oops, where did that come from? And how do I get rid of it? There it goes, okay. So what we see is essentially a fragmentary rock record representing almost 2 billion years. And if you look at this thing, a significant portion of that time is not represented by any rock record in this area. You have to go other places to sort of fill in the gaps. So how does this all relate? Well, we've now recognized the fact that there have been at least 3 supercontinents in the last 2 billion years. The oldest, recognized in the early 2000s, is known as the Columbia supercontinent, came into existence about 1,800 million years ago, or 1.8 billion, which corresponds to the oldest rocks at the canyon. And it broke apart, started splintering and fracturing about 1.5 billion years ago. On top of that, at about 1,100 million, we find another evidence of a supercontinent, and it lasted for almost 350 million years, and then it split apart. And you can see, of course, that the scale here is a little bit screwy, so these things are actually separated by quite a bit of time. And there's another one that most everybody's familiar with, Pangaea supercontinent. It formed about 300 million years ago, broke apart about 180. You'll notice about a 450 million year gap here, and about a 400 million year gap here. So it looks like over geologic time, there's a pattern. Roughly every 400 to 500 million years, a supercontinent forms together and then lasts for a while and splits apart. And what this reminds me of is that old ride that you see when you go to an amusement park. I don't know if they still have it or not, but it's called bumper cars. And of course, if you go with a group of people and you get on the ride, and the person that's running the ride says, "No, I don't want you to bash into each other," and everybody goes, "Oh no, we're not going to do that." But of course, that's the very first thing you do when you get out onto the area. And so what you could visualize is that the continents, if you like, or the lithospheric plates are constantly pulling apart or banging into one another. And they've been doing this now for perhaps 4 billion years. Interesting situation. We go to the Grand Canyon first, and this is a stratigraphic column of the rocks at the canyon. These are the oldest. These are the ones that are found in the inner gorge, and they are separated from younger rocks by what is termed the Great Unconformity. Okay, and as you work your way up the section into the Paleozoic and rocks, there are other unconformities. So it turns out there's a whole variety of different structural and rock types and unconformity features in the Grand Canyon. It's a spectacular place, basically, to learn almost everything about geology. Okay, and probably you all know this, but an unconformity is defined as a buried surface of erosion. And there are 3 main types, all of which represent there is missing rock record. And if you go online or you hear people talk, they'll sometimes say, oh, an unconformity is a gap in time. And the fact is that there's no such thing. You can have a missing rock record, but you can't have a gap in time. So even though there's an unconformity here, the time still exists. We just don't have a rock record of it. So the main 3 types are nonconformities, angular unconformities, and disconformities. And all 3 of those types occur at some point in the Grand Canyon. And we'll look at all of those. So at the base, down here, this is the inner gorge, and this is the Colorado River. And these rocks are essentially crystalline basement complex. They're known as the Vishnu schist and the Zoroaster granite, although it's more accurate to say it's a Vishnu complex because there's a variety of other different kinds of rocks in here, but they're all crystalline and they've undergone a lot of heat and pressure. And then we have an unconformity, and on top of it are layers of sedimentary and volcanic rocks right here at the top that are part of what is known as the Grand Canyon supergroup. A close-up of these rocks down here. Here is the Zoroaster granite, and here is what is called the Vishnu schist. In this photo, this is actually not a schist, it's a higher metamorphic rock. It's called a gneiss. So it's really the Vishnu gneiss, but that's okay. This was an older rock that was deformed and uplifted and intruded and cooked by this granite. And that occurred about 1,800 million years ago. That's why when you radiometrically date them, both of these rocks have the same geologic age radiometrically, even though we know this is older. Had to be in existence before this came in and brutalized it. Okay, up here we have another picture. This is essentially the Grand Canyon supergroup, and it formed between 1,200 and 750 million years ago. And look a little closer at some of this stuff. What we're going to look at now is basically the entire picture of the canyon. So here we have the Vishnu complex, and then right on top of it in this spot is the Great Unconformity. And on top of that, starting right here with this layer of rock, here are Paleozoic rocks. The oldest is Cambrian, and it's considered to be about 510 million years old. And then, you know, this is about 1,800 million years old. So we're looking at between 12 and 1,300 million years that is hiding in that unconformity, that nonconformity. That's an amazing amount of time where, at least at this spot, there's no rock record. However, in other parts of the canyon, we have those same Paleozoic rocks, but they are sitting on top of not the Vishnu complex, but the Grand Canyon supergroup. And so what we see here is another type of unconformity. This is called an angular unconformity. The rocks below this contact are tilted. The Paleozoic rocks on top are more or less horizontal or flat lying. Okay, so the difference in age here is not quite as much. These are about 200 to 300 million years different in time, whereas these are more like 12 to 1,300 million years different in time. That's why this is known as the Great Unconformity. Okay, the youngest rock unit at the canyon is known as the Kaibab limestone. Okay, it's the youngest basically and makes up the plateau surface in most areas. And within this section of what appear to be continuous rocks, there are at least 2 or 3 disconformities. And we'll look a little bit more of those, I think. We come to St. George, and the reason we do that is we find that a geologic map of St. George shows the oldest rock with this label, PK, Permian Kaibab Formation. So this is the oldest rock exposed in the city of St. George area, but it's the youngest rock exposed at the top of the Grand Canyon. So we have a correlation. We can drive from the Grand Canyon over to St. George and start in right here and then work our way up in this direction, getting progressively younger. Permian, Triassic, Jurassic, and then Quaternary, which we'll come back and look at. These are lava flows, very strange looking fingers coming right down through the city, and a couple of faults just to decorate the place. So a stratigraphic section of these illustrates this. Here's the Kaibab Formation. And then as we work our way up, here's the QB basalt. That's this stuff. And not in the city, but in the local area is this Pine Valley intrusion we're going to talk about. But the main rocks in St. George that you look at are essentially these sedimentary rocks, all of which, except for the Kayenta into the Navajo, are separated by unconformities. The oldest, the Kaibab, is about 270 million years. Then there's roughly, I'll go ahead and say it, there's a 30 million year gap in time, just to be obnoxious. But there's 30 million years where there's no rock record, and then the Moenkopi. And another 30 million years, the Chinle, and then about 10 million to the Moenavi, another 10 to the Kayenta, and then it goes right into the Navajo Sandstone, and then it's gone. That's it. So how does this play out with plate tectonics? Well, let's look at a reconstruction of the supercontinent Pangaea. This apparently formed about 300 million years ago when all of these continents sort of came together in one of those amusement park thrill rides, right? Bumper cars. And one of the results of that collision was the formation of the Appalachians in the United States or North America and the Caledonians in Western Europe, okay? Well, now, since there's an Atlantic Ocean, the Caledonians are here and the Appalachians are here, and they're separated by the Atlantic Ocean now. But anyway, roughly 270 to 210 million years ago, this continental mass was pretty much stable. It didn't split apart, it wasn't moving too much. And the result was a nice formation of sedimentary rocks. And what I illustrated here is that in some intervals of time, there were marine sedimentary rocks deposited here. And in some intervals of time, by the brown, there were terrestrial or marginal marine sedimentary rocks. And so what was going on here was that this was an area of changing from ocean to land, to ocean to land. And if you were wondering where California was, it was here. So it wasn't here, all right? And this basically would be St. George. You'll notice another thing about this. Low latitude, St. George at that time was about 15 degrees north of the equator, which would put it in semi-tropical environments, climates. Okay? So here's another cross-section of what it looked like, say at the level of St. George at the time, going from west to east. So here's the Appalachian Caledonian mine. This is mountains, I mean. This is where these continents collided. And what I've shown here with this arrow is that the oceans transgressed, made deposition, regressed, caused erosion. Transgressed, more deposition, regressed, caused erosion. So that's where these unconformities are coming from. And they occur on both sides of the continent. All right, so let's look at the rock record. And we find this travel agency named Gullible's Travel, kind of subtle. And here's a possible trip you can sign up to go to. the St. George Geological Wonderland. So we're going to look at the Kaibab Formation. About 270 million years ago, there it was, roughly 15 to 30 degrees north of the equator, and it was pretty much an ocean. The rocks at the Grand Canyon, nicely bedded, kind of light brown limestones and dolostones. In St. George, the same rock, not as well exposed here, but it's the same rock. It has the same kind of fossils, same coloration, and so on. So here are the two locations. There's A on the Colorado Plateau, and here in St. George, B, we're right on the boundary. This is the boundary of the Colorado Plateau, and that's where St. George is sitting right there. Mostly calcium carbonate and dolostone, calcium magnesium carbonate. Okay, here's a weathered surface. These are chert nodules. And here's a fresh surface, and there's a brachiopod fossil and a few other kinds of things floating in here. Most of them are kind of fragmentary, but they are still identifiable. And here's some examples. And what I did here is take, for example, crinoids and show you what a modern one looks like. These are what you mostly find here on the Kaibab. Brachiopods, and here's a more recent one that you see a better picture of the shell. Mollusks, here's a more recent one. You can see what the shell looks like. Then we have bryozoans, we have corals. So a variety of organisms that we know today all live in the ocean. Therefore, we can make the assumption that this limestone and dolostone, based on the fossils, based on the lithology, must have formed in an ocean. And there it is. This is probably what it would have looked like from St. George City Hall if the building was tall enough, about 270 million years ago. Essentially a huge widespread seaway. It extends all the way over into what we know in California and farther east even. So extensive, low latitude, warm water, teeming with fossils. Quite different than what we see today. When we progress, we find that the top of the Kaibab with the contact of the Moenkopi is an unconformity. And the Moenkopi is also a marine deposited sedimentary rock, but distinctly different, not only in age, but in fossils, but in composition. And here's a picture of it. Here's a nice exposure of the Moenkopi in St. George. On top of it is a conglomerate that we'll be talking about next, part of the Chinle Formation. Mudstone and siltstone, ripple marks in fine-grained sandstone. It even has gypsum. And there's a place here in St. George called the Glitter Pit that's basically been quarried for gypsum. And here's some examples of it. It's a very, very translucent mineral, and it's very soft. You can actually scratch it with your fingernail and almost see through it. It's translucent. But one of the interesting things about it goes back to this gypsum here, is that this gypsum not only forms in water, but it dissolves in water. It's an evaporite mineral, and it forms in hot and arid saline climates, typical of what we would have seen here in St. George if we were living here. So in the Moenkopi, we have various kinds of starfish, brachiopods, bivalves, and so on and so forth. And they are found in the limestones, which are normal marine conditions, but interbedded with them are clearly more terrestrial environments, suggesting estuaries and channels and low-lying land. So quite a variety of variations here, along with that gypsum. And there it is, Tidal Flats. So some modern pictures to show what it might have looked like. Here's a good example in the Middle East. Very shallow water, very hot, high evaporation, high temperature. Same thing here, estuaries. So these are probably examples of what it might have looked like 240 million years ago. Turgidous clastics in shallower environments. Limestone a little bit farther offshore. Gypsum very close to shore resulting from evaporation. And sandstones brought down perhaps by rivers and deposited in these estuaries. and stuff happens. So about 200 to 190 million years ago, the bumper cars came apart. And apparently, energy below the surface caused Pangaea to start cracking and pulling apart. And what we see as a result of that is extension. And when you get extension like this in the lithosphere, you end up with normal faults, volcanism, and tilting of the previous rocks. And these structures are similar to what we see today in what we call the Basin Range Province and in the East African Rift Valleys. So roughly 200 to 190 million years ago, the center of the continent was starting to pull apart. And if you were barely, you'd probably hear it cracking and creaking and volcanoes erupting and all kinds of stuff happening. And we also have deposition of a terrestrial deposit known as the Chinle Formation. In the St. George area, the base of the Chinle Formation, which overlies the bone copy. Now remember, this is an unconformity. There's about a 30 million year difference in age between these two rock units. And this conglomerate is known as the Shinarump member of the Chinle Formation. On top of this is what is known as the petrified forest member, and it consists of mudstones and shales and what is known also in local areas as blue clay. Okay, clearly a different energy of depositional environment. This rock is very resistant to weathering, so most of the ridges in St. George, if they're not covered by volcanoes, are topped by the Shinarump member of the Chinle. So what we see in the Chinle are these conglomerates. We also see coarse grained sandstone with fossilized logs, and we see cross stratification or cross bedded, very coarse grained sandstone and ripple marks. So this all suggests various kinds of stream channel floodplain deposits, enough energy to bring fairly decent sized boulders and clasts and sand down, current to produce ripple marks and the cross bedding, and presumably during floods, bringing down trees that get deposited and become silicified. So floodplains and streams. In the mudstones, we find more evidence of terrestrial environment. We find various kinds of plant leaves, okay? In some of the areas, we find some freshwater fossils, and we even find some terrestrial vertebrate remains, some early dinosaurs and such, and here's some examples. Here's what is known as a phytosaur, perhaps an ancestor in living terminology to crocodiles and alligators. Freshwater fish and small early dinosaurs. So here's my view of St. George, say 200 million years ago. Doesn't look at all anything like the Kaibab, doesn't look anything like the Moen Kopi, and it looks like a very lush, warm, watery place. And that's what it was, okay? And so here is this location. And this is kind of a reconstruction of what it might have looked like. Very lush environment, sort of a kind of like the Florida Everglades today. The Moenabe Formation, again, another unconformity, and the Moenabe terrestrial. And as you can see, Pangaea is kind of starting to split apart. The southern part of the Atlantic Ocean is starting to break apart. The central is spreading apart, and the northern part is creaking and grinding and moaning, but it hasn't quite split yet. And what we find being deposited on the west end of the continent are terrestrial deposits that have an amazing amount of dinosaur tracks. And in St. George, we now have the Dinosaur Museum, which was discovered by, the fossil footprints were discovered in the early 2000s by accident. A fellow was backhoeing here, flipped over a piece of sandstone and saw these footprints and realized the significance. And this land was then donated to the city and such, and has become essentially a world famous location. These Triassic dinosaur trackways and other associated features are some of the most spectacular of anywhere in this particular age, anywhere in the world. So it's a pretty amazing place. And there's a building that was built and opened in about 2004 or 5, if I remember correctly. And all of this area has been excavated, and you realize, of course, that all these buildings and all this area here are probably covering up more of this formation that nobody realized what was in it. So this was a pretty widespread environment, and we only have a fraction of it, yet this fraction has provided a world record or world-class museum. And here's an interior of it. Essentially, the floor of the museum is the bedding surface of these rocks. And it's just loaded with footprints. And here's some reconstructions of some of the critters that made these things. And if you come here on your field trip, you got to go to the museum. That's on your bucket list. Here's the reconstruction of the environment. This is known as Lake Dixie. And I suppose since they're changing the name of the university, they may have to change the name of the lake. I don't know. We'll have to see. And here's the dinosaur tracks. And what's interesting, the way they reconstructed this, the tail is dragging on the ground. And if you go into the museum, in one spot in the museum, you can actually see this tail drag, and you can see its butt print. So this thing left footprints and its butt prints in the sands of time. Pretty incredible stuff. When you go there, you'll also see a lot of tracks and footprints that don't make sense. When you walk on mud or sand or whatever, you leave footprints, impressions, right? But yet most of the fossils that you see there, the majority of them are positive relief rather than negative impressions. And what's going on here is this. This is where the animal walked. Another layer of mud or sand was poured over it, filled in, and preserved the tracks. When these things are split apart along the bedding plane, this is what you get on the upper surface when you flip it over, and this is what you see on the lower surface. So the original and the molds made out of the casts made out of the original molds. What we also don't know, and one of the interesting things about this museum, is that there are very few dinosaur bones there. So in reality, we don't know exactly which dinosaurs made which footprints. And if you think about it, if you go down to a lake or a river today, you'll see all kinds of bird tracks. And if you don't see the actual birds there, you don't know which birds made the tracks. So what paleontologists decided to do was to give the trackways scientific generic names based upon their size. So growlators are the smaller ones, eubrontes are bigger ones. And in the museum, when they have as a display, they have a eubrontes, and then right next to it, a diagram of a mold, a specimen of a brontosaur, if you want to remember that name, a big sauropod footprint. And this thing is dwarfed. You could literally sit in it and take a bath in that dinosaur footprint. They're amazing. So another unconformity, and we creep up about 190 million years ago into the Kayenta Formation. I didn't find another map, so I used the same one, but there's actually, at this point in time, there's starting to be Atlantic Ocean. And here are some examples of the Kayenta. This is the Interstate 15 road cut right in the center of St. George. This is a close-up of what the rocks look like. And here at the corner of St. George Boulevard and Bluff Street, there's a beautifully exposed river channel. This is basically mudstone and siltstone, and here's a layer of sandstone with a clear pattern indicating this is a cross-section right across an old stream, 190 million year old stream. All right, another interesting thing is on top of the Kayenta, at this spot is a lava flow, basalt, which is no older than 2.5 million years. So this contact represents about 190 million years. No rocks. This is a reconstruction based upon the rocks and the fossils. This is a diorama of what it looked like here. Pretty amazing stuff. We have ginkgo fossils, and by the way, you can go buy a ginkgo tree if you want one in your own garden. They were thought to be extinct, but in the early 1900s, they were discovered growing in China, and they've now been exported all over the world. They're really, really pretty trees. If you get a female ginkgo, it's a bad thing when they start producing spores and pollen for reproduction because they have an odor to them. But otherwise, they're really pretty. Living cycads, they occur in this formation, and they still exist today. This is what dinosaurs were eating. So what we see in the Kayenta are a variety of freshwater invertebrates, a whole variety of different kinds of plants, including petrified wood and such, sharks in the water, amphibians and reptiles in the land, small mammals and numerous dinosaurs, and a bunch of trace fossils, dinosaur poop, maybe other organisms as well, and a variety of different footprints and trackways. So truly, the Kayenta Formation was actually a real Jurassic Park. And then we get to 180 million years later, or 180 million years ago, about 10 million years later, we now have a North Atlantic Ocean. Okay, so, and we know that because these rocks right here, if you go right to the edge of the continental shelf, right before it becomes continent, these ocean floor basalts in the Atlantic have a maximum radiometric date of about 180 million years. So that's when we know the Atlantic Ocean finally started opening in the northern hemisphere. Okay, so this was moving westward, and it was crashing into the Pacific Ocean lithospheric plate, generating subduction, which generated heat, and we got a variety of different features. Okay, so we got starting to get mountain building here. The Appalachians are busily eroding away. And what's going on here? Well, we come into what is known as the Navajo Sandstone. Again, terrestrial, and you'll notice the continent has moved a little bit farther north. So this is the rifting that started the Atlantic Ocean. And we got subduction. And at this latitude, we get into what are sometimes known as desert areas. We have them today. In fact, the West Coast is typically a desert area when you get inland from mountain barriers. And this is what was deposited, what is known as the Navajo Sandstone, right on top of the Kayenta. No apparent unconformity here. And it's got desert varnish, and it's got vertical joints, and it forms nice vertical cliffs, which are beautifully exposed at Zion Canyon. The interpretation, based upon what we see in the Navajo, is that it was essentially like the Sahara Desert today. It had some water areas called oases, and it was widespread, a little bit in California, Nevada, Utah, even to wherever this place is, Wyoming or something like that. Never heard of it before. Colorado, New Mexico, and so on. A huge widespread, what they call the Navajo erg. And one of the distinctive features are these crossbeds, which represent ancient sand dunes. So we see in the oases, little bits of limestone with some freshwater fossils. We see some mud cracks where the areas were drying out. And in some of the local areas around these things, we see dinosaur remains and trackways in the sandstones. But primarily what we see are crossbeds, an ancient dune field. Okay, so sort of summarizing some of this stuff. About 542 million years ago, we begin in a fossil record. And at that point in time, we have no rock record at the Grand Canyon. But right above that are some of the rocks of the Grand Canyon. And as we work our way up, we find another unconformity, a disconformity, but it represents a pretty significant amount of time. Uppermost Cambrian, Ordovician, Silurian, and a good portion of the Devonian are not represented at the canyon. And by the time we see more rocks represented by Mississippian and Pennsylvanian, Pangaea, the supercontinent, was beginning to form. And so these represent the uppermost part of the canyon that we saw at the beginning, which a bunch of disconformities, but a relatively significant fossil of rock and fossil record. And then we discover at the end of the Paleozoic, worldwide glaciation, a supercontinent, and a mass extinction. And the results of all these things was, at least in this part of the world, erosion. So we have an unconformity that marks this boundary. When we get into St. George, we find some of these rocks right here that we mentioned, and then a significant number of rocks that we just looked at. And then up in this area right here, about 180 million years ago, Pangaea starts to fall apart, separates. And we get into Zion Canyon rocks. So these are the oldest rocks at St. George. These are the youngest. When you drive over to Zion, you'll start right in on this area here. And then a big unconformity, another mass extinction event, followed by the rocks at Bryce Canyon. And then the west side of the continent in the last 60 million years or so has been uplifted to what we see today. And more glacial episodes. All right, so a real quick summary. Pangaea, stable. Pangaea starting to fall apart. Pangaea moving across and subduction. Kaibab Formation. Wide ocean. Unconformity. Tidal flats of the Bowen Copy. Unconformity. Chinle Formation. Lake and river systems. Unconformity. Moenavi Formation. Dinosaur land. Widespread lakes and rivers. Unconformity. Kayenta. Deposition in rivers and streams, followed by a desert. So roughly 90 million years. Some of it represented by rocks, but a good portion of it represented by unconformities. Interesting, but frustrating. It's like reading a book with chapters missing. So we jump over to Zion, and we're just going to summarize it, essentially. The rocks at Zion are essentially from late Triassic up through late Jurassic. Most of the park is made up of the Navajo Sandstone, this widespread sand desert erg. Below it, the Kayenta, a little sandstone snuck in that's a little different than St. George. But then we have our Jurassic Park, then we have our desert, and then we have an ocean again. In late Jurassic, the ocean spread across the western part of the United States. It's known as the Sundance Interior Seaway, and it preserves some of the most spectacular marine fossils and on its banks, terrestrial fossils of anywhere in the world. If you've ever seen dinosaur collections and you've ever heard of the dinosaur collectors named O.C. Marsh and E.D. Cope back in the late 1800s, a lot of that stuff came out of this Sundance Seaway. It's a spectacular place. And then we jump to Bryce, and we find another interior seaway, but this one's Cretaceous in age, and it does the same thing. An amazing amount of fossil remains, both marine and terrestrial. Huge marine reptiles, huge terrestrial reptiles, spectacular place. And then as you work your way up into the rocks that actually make up Bryce Canyon, we find a regression and we start seeing essentially terrestrial freshwater lakes and such, but the kinds of fossils that we see in them are different than what we saw in those lakes in the St. George rocks. Right? So here's the Claron Formation that makes up the major portion of Bryce Canyon area. And of course, it's spectacular weathering. That's what makes it so distinctive. So to summarize this in a nice, crazy chart, here's Grand Canyon National Park. Here are the rocks. Here's the St. George area, starting with the Kaibab and ending with Navajo. And then we have this rocks at Zion. And then above that, we have an unconformity, and we get into the rocks at Bryce. And if you're familiar with it, this is known as the Grand Staircase, with the chocolate cliffs, the vermilion cliffs, the white cliffs, and the gray cliffs. Another spectacular area to look at when you're here. And what we do then as geologists is try and put all this stuff together. So here is kind of a widespread correlation going all the way from Grand Canyon to Zion to Canyonlands and so on. And what we're seeing here is essentially a section of rock, correlation, 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 and correlation. And of course, these things aren't suspended in space naturally. They are essentially, if you wanted to get a permit, you could drill through here and find, if you went down through here, you'd find some of these older rocks. So what we're seeing essentially is a succession of roughly 2 billion years worth of rocks. And I don't know if there's anywhere else in the world in such a confined area that you can see that so well exposed. It's a spectacular thing. And we get back to St. George, and we're going to go into a different realm, basically, and we're going to look at some hot times. And what we are going to look at now is a record of volcanic activity over the last 25 or so million years. So this is a diagram showing heat. Again, where did this heat come from? Probably from nuclear fission, radioactive decay, and it generates two basic kinds of rocks. Those that form and cool below the surface called intrusive, and those that form above and on the surface called extrusive. Yeah, I know it is kind of confusing, but it's okay. We'll explain it. What's going on? Well, there you go. 25 or so million years ago, we had a collision, the ongoing collision. But today, when you discover beginning about 25 or so million years ago, this collision stopped. And roughly from San Francisco south to the Sea of Cortez along the west coast, there is no collision. There's no trench. When you go north of San Francisco and you go off the coast up into Canada and Alaska, this is still going on. But what happened here is we literally overrode what was known as the Pacific Spreading Center. And we now have the San Andreas Fault. So there's no collision, but there's still heat down here. And that heat is generating igneous activity. This is the Pine Valley Mountains, and this exposed structure is known as a Lacquer Lift. These rocks cooled below the surface about 22 to 23 million years ago and formed a quartz monzonite, and you can see the crystals in this stuff. So fairly coarse-grained, intrusive igneous rock that in the last 22 million years has been exposed by erosion of the overlying sedimentary rocks. So here's a diagram. Here's what it looked like maybe 22 million years ago. And these rocks, sedimentary and not that sturdy, have become eroded, exposing what we call a laccolith. And the shape of this thing, this kind of semi-mushroom shape, is why it's called a laccolith. And it may be, and I don't know for sure, but a lot of people think that this is the largest laccolith in the world. So, I mean, how can you beat this, right? We got maybe the biggest laccolith in the world. We got the most spectacular dinosaur remains. We got a spectacular Sahara Desert here. We had an ancient seaway. What more could you possibly want? So we go back and look at the volcanoes here. These are lava flows. I've heard some people argue that what those really are, they represent the remains of ancient alien highways. I guess that's part of what they call multiple working scientific hypotheses. But it turns out that this is just a small fragment of what's been going on here for the last 20 to 30 million years. Each of these rectangles represents a volcanic field. And this is the one right around where we're looking at. Here's the one farther east, and then here's one in Nevada and in southeastern California. These tend to range in age from about 25 to 30 million years ago to some around St. George that are less than 2.5 million years old and maybe as young as 10,000 years. So there's clearly still heat coming down at the surface here. And here's a cinder cone and a lava flow up Highway 18. There's Highway 18, and right up here is the turnoff to Diamond Valley. Here's a perfect Hollywood example of a cinder cone and a lava flow. And then here's an example of one of those alien highways. And you look at that, and it really does look like an old highway. All right. What you're seeing here is essentially a liquid lava flow that in St. George was spectacular because it flowed down the top of a ridge, but didn't flow down the sides. And you go, well, wait a minute, that's impossible. And you're right. So what we're looking at here is an ancient stream bed. And the lava flowed down that ancient stream bed, cooled and solidified and hardened. And just like with the Pine Valley Mountain, the surrounding sedimentary rocks have been eroded away, leaving this lava flow sticking up as a ridge. And it's called inverted topography. So this is a stream valley that's now sitting up as a ridge. Kind of bizarre. Close up, here's this lava flow, and there's two basic kinds. There's vesicular basalt, and there's what we call massive basalt. They're identical in composition to what you see in Hawaii. And speaking of that, if any of you have ever been to Hawaiian Islands and you've gone to see a green sand beach, that sand, that green sand, is made out of a mineral called olivine. And lo and behold, we have some of it here in our lava flows. There's a little mineral called olivine. It's a semi-precious gemstone, and it's a very pretty green color. So if we look at how that happened, here's a Walt Disney time lapse of how those ridges formed. Between 2.5, 2.3 million, and 20,000 years ago, we had lava flows coming down some of these rivers or streams. The flows solidified and hardened into hard lava or basalt. And then these sedimentary rocks got eroded, and I built a house on top of them. Okay, so this is essentially an inverted lava flow. That's the history of it. And that brings us to the end. And I thought this was a very good saying. Parallel lines do have a lot in common, but they just aren't going to ever meet. Okay, so we're prepared now.
Wow, Rick, this is Mike Scher. I'm doing the questions, and you've done an incredible job explaining very lucidly 2 billion years of Earth's history in the Western United States. And so let's start with some questions. One of the sort of obvious questions, I think, is that there's deformation on all sides of the Colorado Plateau, but the Colorado Plateau itself is basically undeformed.
Yeah.
Except, I mean, there are monoclines in it, further east of you. But could you talk about this sort of island of stability in the middle of this huge mess?
Yeah. Okay. Well, basically what happens is the Colorado River, the plateau essentially has been uplifted, and they've argued that it's gone different phases of uplift, beginning 60 million years ago, and then maybe again between 10 and 6 million years ago, and continuing a little bit today. When that started, what we call the basin and range today was essentially part of that uplift. But what's happened is that for whatever reason, underneath what we now call the basin and range, extension has occurred. So there's a heat source coming up. You know, when you put a pot of water on a stove and you heat it up and the water starts to boil, then it comes up and then it spreads out, kind of convection. All right, so that's what we're seeing happening under the basin and range. And it didn't extend far enough east, so it preserved part of what was that Colorado Plateau. Okay, so the extension essentially ends at a fault that marks the beginning of the Colorado Plateau. All right, and it's a Wasatch fault system that goes all the way up diagonally through Utah. And essentially, the Grand Canyon kind of escaped that deformation. The extension goes essentially west of the Colorado Plateau and is pulling the basin range apart. And if you want a good analogy of that, go back, say, 190 million years ago to when Pangaea split apart. You had the same thing happening. And what you see preserved on the East Coast area, if it's not covered by younger sedimentary rock, is the same normal faults, volcanism, and tilted layers of sedimentary rock. And the same thing is happening today that form the East African rift valleys. Literally, the continental lithosphere is being pulled apart, extension. The crust thins and tilts and breaks, and that allows the heat to come to the surface and form volcanism. Does that make sense?
I think it makes sense to me. I hope it makes sense to the other participants who asked this.
There's going to be a quiz next Monday, so.
Okay. Well, we'll study hard. Can you talk about how the heat that you're describing, which is the driving force here, how is that created? In other words, is the subduction creating it? Is it dewatering? You know, what's causing the heat and the melting that's feeding all this?
Okay, it's essentially, it's a two-pronged thing, the way I see it, is the western movement in North America generated the subduction, which generated the heat to begin with. And now, even though subduction is not occurring, we have a source of heat, like Yellowstone. There's a hot spot under Yellowstone. Why it's there, we don't know that, all right? There's a hot spot under the Hawaiian Islands. Why it's there, we don't know, all right? There's one of the questions. We understand what's going on. Well, one of the things we don't know is why does a hot spot suddenly decide to form in the Pacific Ocean and have all these islands pop up? Why does a hot spot form under the continent and form the Yellowstone calderas and volcanic structure? Why is there still a hot spot under the basin and range? Why are they there? Presumably it's nuclear fission, but why it's concentrated in that area and when it started, I don't know if anybody knows the answer to that yet.
So the subduction itself is not creating the heat per se. In other words, it's not a frictional process.
Well,
that's what the question.
Okay, the subduction did cause heat. That subduction is what generated, say, the Sierra Nevada mountains. Okay, that subduction, which is going from Northern California into Canada, is what's producing the Cascade Range mountains. That's the heat from subduction. But as you go inland and as you go farther south, we don't have subduction. So these other areas are literally, I think, nuclear fission hotspots. And why they're there, maybe it's a result of subduction, but nobody really that I know of knows for sure yet.
Okay. Can you talk about why there are native silver deposits in the Hurricane Utah area?
I understand, well, like at Silver Reef, for example. You're talking about that, the mines up in Silver Reef. And the silver there, I think, and I'm not going to answer that because I'm not exactly sure the genesis of that. I was thinking it might be placer silver that was deposited like placer gold was in California by streams and rivers, depositing it along with sedimentary rocks. But I would be guessing. I'm not sure.
The great unconformity that you describe in the Grand Canyon, we have a similar, just much larger unconformity here between our crystalline basement rock and then our flathead sandstone. What's the relationship there between this big unconformity across 1,000 miles of Western North America?
Well, that great unconformity, you can see it right outside of Las Vegas in the Frenchman Mountains. You can see it in Arizona as you cross from Utah into Arizona. It's exposed there, and it's exposed up in your area. And I think it's all part of the same major erosional event that happened between the formation of the supercontinents and their breakup. You know, so depending on where you are, if it's still preserved, you have crystalline basement with a sedimentary rock stacked up on top of it. And it represents a huge chunk of time. It's mind-boggling to think about it, over 1 billion years and there's just nothing there.
So is there a relationship between, in other words, the tapetes in your area and what we call the flathead here, which are approximately the same age and deposited right on that basement rock?
Right.
Is this all the same process, or are these rock units really the same with different names across this north-south?
That's pretty much what I understand is there's a couple of Cambrian sandstones in California that are given a different name. And there's here, of course, in the Grand Canyon area and upper near area, they're given different geologic names, but lithologically and time-wise, they pretty much all represent about the same time, about 510 or so million years ago. And what I think we're looking at is essentially what is known as the Cambrian transgression across a continent that was eroded almost flat. And an analogy I think of is if you're familiar with up in the Canadian area, the Canadian Shield around Lake Hudson Bay and all that.
Yeah.
It's Precambrian rock, but it's in most areas, it's very much topographically flat. And if ocean sea level rose, let's say we melt all the glaciers and we get sea level rising and the oceans are going to spread across that, what we would see would be an example of the same thing that happened 500 or so million years ago on the west side of the continent. So crystalline rocks uplift, hundreds of millions of years of erosion, and then a seaway transgressing. And it had transgressed all the way through Death Valley area into Nevada, into Utah, and into Colorado, and up into Montana and Wyoming.
Right. To change the topic slightly, the colors in the Claren Formation in Bryce Canyon are absolutely striking.
Yeah.
Can you talk a little bit about that?
It's iron, baby. I learned that term when I was in Texas for a while.
Oh.
I went to grad school in Texas, and I learned about iron, and I also learned about all. You know what all is? It's that stuff that you drill in and pull out of the ground and distill into gasoline. And in Texas, it's called all. I always thought it was a detergent, but according to Texans, all is that stuff that comes out of the ground. But anyway, wait, what do you want me to answer then? I got sidetracked here.
The brilliant colors in the Claren Formation.
It's iron oxide, red beds. And that's one of the things about the Western United States. We're famous for red beds. And those red beds are essentially a function of oxidized iron. And so what you see are sedimentary rocks that accumulated various kinds of sand grains, some of which may have been iron-bearing minerals. When they're exposed to water and oxygen, they rust. And the amount of iron and the amount of time they're exposed tends to determine how rusty they get.
Another sort of mineral question, further east in Utah, my understanding is that the Chinle is mined for uranium.
Yes.
And are those deposits present in St. George, and why is the uranium in there?
Well, as far as I know, there hasn't been any discoveries of uranium in the Chinle area or in around the southwestern Utah, but it occurs in eastern Utah and kind of extends kind of northeastward up through Utah. So essentially the uranium deposits here in Utah back in the 50s was like the California gold rush in the 1850s, okay? And a guy named Charlie Steen who discovered them, and he found the bonanza there. And as far as I know, those uranium deposits are, again, the result of stream deposits. You know, the uranium was concentrated into placer deposits, and why they aren't here in this part of the country, but are in the eastern part of Utah, I don't know. But yeah, during the uranium boom, it was an amazing place.
Right. And so going back to the dinosaur tracks diagram that you showed us, the overlying positive or proud tracks,
Mhm.
those rocks would have to have been flipped over for us to see them. Is that a correct interpretation?
That's exactly how they discovered it. A fellow named Sheldon Johnson, who is a doctor, owned that land, and he got his backhoe out. And he was going to bevel it off and get it ready for selling for property, whatever. And he flipped over a big hunk of this sandstone with his backhoe. And when it landed on the surface, he looked down and he saw all these positive dinosaur tracks. And he went, "Oh, okay." He realized what they were and called in the paleontologist, who freaked out. I mean, literally, it was one of those once in a lifetime discoveries. It's unbelievable, and it's sort of an interesting side to that. When you go to what is known as the Triassic Connecticut Valley area in New Jersey, okay, there's dinosaur tracks there that have been known since I think the late 1800s or so, and they are the same kind of tracks that we have here.
Wow.
And it's roughly the same age rock, and it's basically the same kind of rock.
Right, Triassic mud.
Yeah. And they don't have any bones there either.
Right, unfortunately. So in the geologic map you showed of the St. George area, it looked like there was an anticline running north to south through St. George. Is that a correct interpretation?
Well, actually, no. It's not really an anticline because the rocks are pretty nearly just slightly northward tilted. It's more of a monocline.
Okay.
But there is an anticline south and east, the Virgin Anticline, that runs south of the city. It's just off the picture, but that's been folded. But the St. George Rock area is basically a monocline with the Permian and all the overlying rocks tilted slightly downward in a north direction. So if you drove up in St. George, what we call River Road, you'd essentially be going through oldest to youngest on the surface. And if you look up this St. George self-guided field trip that I've got on available online, you can actually follow that.
Okay. So one question is, do you run tours yourself through the Virgin River area and the canyon?
I haven't done any of my own, mainly because, and the reason I didn't go on this trip you guys are doing is my house has become a sanctuary. I must have 30 different kinds of animals and plants there, and I don't have anybody that'll take care of them for overnight or over a few days. So I'm kind of stuck.
Okay.
But I have put together this virtual, well, it's not virtual, but an actually self-guided field trip that takes about 3 hours to see most of the things I talked about in this talk.
Okay. So the last question is sort of a softball question, I think. Why is Dixie State changing their name?
They feel like the name Dixie is a reflection on the Dixie cotton in the South associated with the slavery. And one of the interesting things about that, it reminds me, is I've talked to people all over the country about stuff, and every so often they go, "Well, what do you do there?" And I says, "Well, I do a lot of teaching at Dixie State." And there's a silence on the other end of the phone, and they go, "I thought you lived in St. George." And so I don't know why. It would seem logical based on coming from California. Why didn't they call it Utah State University, St. George? But
good question.
I mean, it modifies St. George and it helps the city, and it's a state university. So what's the problem? But it's just interesting to think how people are thinking about it. Anyway.
Right. Well, Rick, I want to thank you on behalf of all of us at the Geologists, the Jackson Hole, for a fabulous tour of Southwest Utah. Can't wait to get back down there. You've covered an amazing amount of ground, and you did it with our timeline, which was a lot shorter than 2 billion years. So
okay. One quick question is I think I sent to John and to Mike a link, a OneDrive link. I had a longer presentation,
right.
and I got the comment that said, "I don't know if you could do that in an hour." So I've cut out about 8 or 10 slides, but they're still on that OneDrive link. So if anybody
Okay.
wants to look at that, I'm welcome to send them the link, or if you can send it to people, that would be great.
Yeah, no, we have that and we can absolutely do that for
right.
anyone who's interested. So I want to mention that in 2 weeks' time, we're going to get a Wyoming tour, you know, that state that Dr. Miller refused to mention, from Carol Frost.
Yeah, I
of the
saw that.
University
Yeah.
of Wyoming. And it will be an excellent talk by someone who knows Wyoming geology probably as well as anyone in the world.
Awesome.
And Dr. Miller, you're welcome to join us as well for Dr. Frost's talk.
I think I may do that. Yeah, and will you send me the info? I saw it when you had the introduction, but yeah, make sure I'm on the mailing list.
Yes, it'll be an in-person talk with a Zoom link.
I'm jealous.
So everyone, no matter where you live in the world, can watch it.
Awesome.
So thank you, everyone, and especially Dr. Miller for a wonderful talk. You make us all want to run down to Utah when it gets a little bit cooler.
Yeah, for sure. It's 107 today, I think. Not fun. Okay.
No, we'll take the 80 degrees here.
Yeah, no kidding. All right.
Okay, thank you, everyone, and good night.